Hey,
Hi, how's it going?
hey, good. Cool. I was just looking over your details. This is for a junior engineering position. Is that correct?
Yes. So it's
Correct.
probably for an SDE2 position. I'm not
Oh,
sure. I think that might be mid-level for Amazon,
yeah.
but I would probably be looking to enter in as a sort of lower level SDE2.
Okay. Okay. All right. I guess that I would usually consider that more on the senior side. Yeah. Um, okay. Well, okay. Maybe I'll pick a different question then. Okay, cool. Let's go with this one. And yeah, and if we have time, we'll do another question, or I can follow up with some follow up questions.
That sounds great.
All right. And then you can just pick whatever language you'd like, but I'll post the question here.
Okay, I'll go ahead and choose the language. There you go.
Okay. So let's say you're dealing with a binary search tree. So that means that for each node, it has the following properties where the left subtree is less than the root and the root is less than the right subtree. So when you do an in-order traversal, that would result in going from the smallest element up to the largest element. So let's say I give you a node in the BST. I want you to get me the in-order successor.
Okay. All right, so let's take a look here. So I'll go ahead and just do an example to make sure that I understand the problem. So let's say we have a tree that's 5. Oops. 7.
Yeah.
And 2, 2. And let's see, 4. Okay, so here's an example binary search tree. This one happens to be balanced.
Mm-hmm.
So let's say that you gave me, so a binary search tree and inner traversal would result in the node sorted ascending order smallest to largest. Given any node in a BST, get the in-order successor to that node. So let's see, the successor is the next node in the traversal. You can assume the node is valid and exists somewhere in the tree. Okay, so let's say that we're given 5, the root node. We would want to return 6.
Mm-hmm.
Another example, given, let's see, 6, you want to return 7. Okay, let's see. Given 8, an edge case here, we would want to return none. Does that work for you?
Yeah.
Okay. Let's see, any other interesting cases? Okay, so that's the gist of it. We'll assume that our BST is well formed, so we don't have to check to make sure that the BST property holds. Let's see. Okay, if I think of any other edge cases, I'll keep track of them here. But
Yeah, you can make that assumption.
Okay, great. So, okay, I think there are a couple cases here. So there is the case, BSG, I guess sort of a brute force solution is to traverse the tree in order and store each node in output list, and then we could traverse list and return node after a given node.
Mm-hmm. So what would be the space and time complexity of that? Yeah, looks like you were already doing it.
O of 1 time complexity, because we're just going to, well, it's really O of n plus n, but that simplifies down to O of n. And then, but our space complexity is where we take the hit, because now we've got to traverse the tree and we've also got to store it in an output and array. So I think that really our best conceivable runtime from a time perspective is to hit, let's see, we should be able to do some type of binary search, given that it's a binary tree. So we shouldn't have to traverse every single element. So I think it's feasible to shoot for something in O of log n time. And then depending on how we implement it, if we do it recursively, our space would be O of log n. Or if we have an iterative approach, we might be able to pull it off in O of 1 space.
Okay, so let's talk about some improvements you can make to the brute force. Let's try to improve the time. I'm okay with the space being either. But yeah, let's talk about how we can improve the time.
Okay, great. So what we can do is a typical binary search through the binary search tree. So what we can do is try to find our given element and then maybe do some extra processing or keep track of a couple of different elements that will allow us to find the successor. So what we can do, let's see. So just walking through this example by hand, given 5. So we have found, in this case, the root node is the node we're searching for, and there is a right child, which means that we will return the right child. So, excuse me, that's not the case. So let's talk about the different cases. So there's a case where I'll call it the search node. Search node has right child, get smallest element in right subtree. So that's the first example there. We see that we have 5. 5 has a right child, so we want to get the smallest element from that subtree, which will be the next, which will be the in-order successor to that node. Let's see another case here. Given 6, we return 7. So in that case, let's see. So we find 6. 6 does not have any children, or I should say it doesn't have any. So we'll say if node has no children, then we want to return the parent, because the parent will be the next larger element. Okay, let's see. And then there's also the case where we do not have a successor. Let's see. So we, our search node has no children, and in this case, we will return none. Okay. So walking through our example, let's take another one. Let's take 3. So applying our algorithm, we do typical binary search. We see that 3 is less than the root node 5. So we traverse left. We see that 3 is the node that we're searching for. So find the minimum element in its right subtree, which is 4. Okay, so that works. Let's see. Let's say that we're given 7. So we traverse the binary tree, find 7, and then we want to, let's see, find the smallest element in the right subtree, which is 8. Okay, so this looks good to me. So I'm going to write out a little bit of pseudocode here.
Okay.
Okay, so what we want to do, let's see. So we'll have a recursive function, and we'll, let's see. If current node, let's see, it's going to basically be walking through the cases. Let me just think for a moment if there's any anything I haven't considered. Okay, I think that the cases kind of handle my pseudocode, so I'm going to go ahead and jump in.
Okay. Can you explain each case very briefly?
Sure. So basically what we're going to do is we're going to search our binary tree for the element. I think another assumption that I need to list is that we need to find out if that node exists. Should I assume that that node exists in the tree, or that it could be? Okay. Oh, there it is. Okay, thank you. Great. Okay, so we're going to do a binary search to identify our node. Once we find the node, there are a couple cases we have to consider. In the case where the node has a right child, we need to return the smallest element in the right subtree, which is the smallest element that's larger than our search node. If that node has no children, oh, I see. I've repeated myself here. Okay. Okay, so when I say if search node has no children, returning the parent is not the thing to do. What I need to do is return, let's see, next largest number. So what I can do is, as I'm traversing my binary search tree, if I traverse left, what I can do is I can save the node at which I traverse left as my next largest number. So that will ensure that if I end up in the case where where my search node has no child, I will have stored previously the next largest number. And I will initialize this to none, which will handle the case where there is no larger value. Okay, thanks for catching that. So just really quickly to run through an example, let's say that we're given 4. So at 5, I see that 4 is less than 5. So as I traverse left, I'll save that node value, which is 5. So 5 will be our next largest number. I'll hit 3, see it's greater than 3, find the minimum element there. Or excuse me, and then I find 4 and see that there's no children, and so I return the next largest number.
Got it. Okay.
Okay, great. And then in terms of, I'll just get the algorithm down first, and then we can talk through some test cases. So we will do.
Okay.
So I'm going to do get successor, which will take a node and next largest. We'll say if, so now our two cases here. Almost on the right subtree. Okay, so if node if the node does not exist, then we need to return next largest. Okay. Let's see, so that's our first case. And then let's see here.
No. Okay, so this is like the return value, is that right?
Yeah, so that's so I'm going to have another helper function up here that will be get smallest given a node, and that will return the smallest. I'll just leave that there for now. But basically, if we've traversed to the point where there's not a node, then we'll return the next largest value. Let's see. If not node, elif node dot right. If let's see, it has a right node, then we want to return. Let's see, get smallest of node dot right. Otherwise, let's see, on node else node. Otherwise, we want to return get successor of node dot left. Next largest will be node dot val. Okay. So I'll revisit this, but just to get my full idea down here. So when we get the smallest for a node, we'll say if not. Let's see here. So if the node does not have a right value, then we will return node.val. Let's see. Otherwise, we will return get smallest of node.right. Oh, excuse me, this is the smallest. So if not node. Okay, so when we get the smallest value, let's say that we're given 7, we want to traverse left as far as possible. So if the node does not have a value on its left, then we know that we have found our minimum element in that subtree. Otherwise, we want to continue traversing left until we found it. Okay.
I see.
Okay, so that will ensure that we get our smallest element. And then when we get our successor, what is it? Okay, so when we get our successor, if our node does not exist, then we know, okay, I need to do the binary search property in here. Okay. So there's one additional layer on here that I need to take care of. Its successor, it needs to be past the node that we found. So we'll say find node, which will take in a node and our value that we're searching for, which is, we'll call it num. So say if node.val equals num, return node. Else, if node.val is less than num, we need to go right. Otherwise, we need to go left and okay. So this function here will return the node in the tree. Okay, hold on. I think that I need to consider my inputs a little bit more closely here. So I'm given a node in a BST. Okay, so when I'm given the node itself, not the value of the node, is that correct?
Yeah.
Okay, got it. So that's sort of superfluous then. I coded this up thinking that I would have the node value, but I have the node itself, so I can just start directly from the node.
Okay, let's hang on then. Let's keep that there. Don't need to necessarily remove it quite yet. Okay, so and I think here you probably meant elif. Otherwise.
Oh yes, thank you. Well, that would just be an
comment this out. But yeah, I see what you're saying. Okay, so where are you going to call find node, or if at all?
I think that's a good point. Find node would only be called if we had the number that we wanted to search for in the tree, but not the node itself. So find node in this example would not be called, yeah.
Fair enough. Okay, so how would I call your function that actually gets me the successor?
Okay, great. So let's say down here, what we'll go ahead and do is, let's say that we had, I'll just kind of make up a, so let's say that search node equals, we'll just say that search node is some node that already exists in a binary search tree. And so I'd say get successor of search node none. And what that would do is handle the case where we do not have a next largest value. So basically, walking through this, so let's say that our search node is, let's say that it's 5. So given 5, we want to find 6. Okay, I see the issue here. Okay. So I'm getting a little tangled up here, but I think I realize what's going on. So it's key that I walk through my binary search from the root node, because if I'm just given a node such as 6, I won't be able to access its parent. So when I do, so I do need to call. Let's see. Okay. I think I need to combine my binary search with my get successor. So basically get successor would take a root node, a search node, and then the next largest. So we have our node, search node, next largest. Okay. So to back things up here a little bit, so when we are, let's see. Okay, I think I need to take just a step back and think about it from pseudocode.
Sure.
Okay, so the first thing that I need to do is traverse binary tree until node is found, keeping track of next largest. Okay. Once I have found the next largest, or excuse me, until the search node is found. Okay, so once I have found the search node, then I have my cases to consider. So if the search node, when search node found, consider 2 cases. Okay, got it. So that's the point at which I would handle those 2 cases. But in the meantime, get successor would have a built-in binary search. So given our node, what we want to do is, let's handle the binary search here. So if search node dot val is greater than node dot val, then we want to first write okay. Else if the search node is less than node, the current node, then we want to traverse left. And when we do so, we want to update next largest, it said. Otherwise, we have the case where we have found our node and we have to consider these 2 cases listed above. So now that we've found the node, if, let's see, not node.left and not node.right, then we can return our next largest. Okay. Else if, oops.
Oh, okay.
Else if we have a right subtree, then we need to return get smallest of node.right.
Mm-hmm.
Okay, so I'm going to go ahead and remove this code here and then take another look and make sure that
Okay. That does seem to line up more with what you had originally stated.
Yeah, I'm sorry about that. I think that it's always good to go through a little bit more pseudocode on the front end. Okay, so in this case, we're doing our binary search. So, let's go ahead and walk through an example here. Let's say that we're given 6. So we call get successor with the root node, our search node, and none. So what we'll do is if our search node value is greater than our root, which is 5, we'll traverse right. Okay, so now we're at 7. So if so now our search node value is less than the current node's value, so we will update next largest to 7, and we'll traverse left to 6. Now I've hit that third conditional where the search node is equal to the node. So we see that our search node 6 has no children, so we'll return next largest, which is 7. Okay, so let's walk through another one. Let's say that it's 8. So in that case, our next largest will never get updated, and it will remain none. And then we will continue traversing right until we hit 8, and we will return none, which will indicate that there is not a larger value in our binary search tree. So let's see. Okay, let's say that our given is 5. So in the case that it's 5, we immediately hit our third conditional. We see that the search node has a right subtree, so we need to get the smallest element from that right subtree, which will be guaranteed to be our successor. So now we kick into the get smallest function given 5. So we pass that 7. So get smallest of 7. We see that 7 does have a left branch, and so we call get smallest of 6. 6 does not have any nodes to the left of it, so we will return 6, and 6 will be the successor to 5. Okay. Well, I see you've added an example down here.
There's one thing about Python that I'm a little unclear on, which is that there does seem to be a situation where even if you fall into this else, you might not fall into either of these cases. And so, what is the expectation if it doesn't reach a return statement?
Oh, okay. Thanks for pointing that out. So. Okay, so I think that so in that case, you're right. There is a conditional here that's not being handled correctly, and I think that let's see. I see. So I think another example. So the 3 cases once we hit our node is that it has a right subtree, in which case we want the smallest element from the right. It has a left subtree, in which case, let's see. If it has a left subtree, so let's try to think about an example in which that's the case. We do not care if it has a left subtree. What we really care about is the right subtree.
Yeah, I think you're right.
So I think
so you can imagine in this example below, if you were to have some value here on the left of 80, it doesn't seem to really affect anything.
Right. Exactly.
For 80.
Right. Okay, thank you. Yeah, that's a great eye. So what we really want to do is if not node.right.
And so what about this method?
This method can go.
Okay.
Yeah,
All right.
it's built into get successor now.
Okay. Okay. And okay. And then if necessary, we could just wrap this in a helper method that doesn't include next largest, and that would be fine.
Yeah.
Okay.
Great point. Yeah.
Okay, no worries. You don't need to do that. Okay. So, okay, I think this seems more consistent with what you were walking through. Even though when you were describing it doesn't match up with what you were describing in the cases. But I think this is the more proper approach. So, what is the time complexity, space and time complexity at this point?
Okay, great. So, let's see here. So at this point, we are not traversing. We are at most traversing the depth of the tree.
Mm-hmm.
So our time complexity in that case is O of log n. And then because this is a recursive function, we will have a space complexity also of O of log n from putting the calls on the call stack.
Okay. So you mentioned so could you imagine a situation where it's not log of n?
Okay.
Either using your solution. Yeah.
So we know that for sure to identify, to find the number in the binary search tree is O of log n, if the tree is balanced.
Mm-hmm.
So if our tree is unbalanced, in the worst case scenario, we could have a tree where all of the elements are increasing. And so our depth of our tree is equal to the length of our tree, which is O of n. So if our tree is unbalanced, then that's the worst case scenario. If our tree is balanced, then it will ensure log n.
Yeah. So is there a better way to represent the complexity?
Oh, okay. So we could say, let's see. So typically you just write the worst case time complexity.
Right.
But you might be able
what I meant, based on what you described, is there a better way to represent the time and space complexity instead of n?
Oh, okay. So instead of n, we could say d. We could say O of d, where depth is d equals the depth of our maximum. Well, that is the definition of depth of our tree.
Okay. Max depth of the tree. Yeah.
Right.
Okay. Now, what if I asked you to get me the in order predecessor to a node? What would change here?
Okay, great. So if we wanted the in order predecessor, we would want to keep track of the next smallest. So our get successor would look like if our search value is less than our node value, or excuse me, if our search value is greater than our node value, we would go right, except we would update our next smallest instead of our next largest.
Mm-hmm.
And then in this, and on line 53, we would just pass down next smallest rather than updating it. Mm-hmm. And we would say, if not node.left, we will return next smallest. Otherwise, we would get the largest of node.left. So it's kind of the inverse approach. Okay.
And it sounds like here you would just kind of you would swap the pointers as well. That would be the same result. Okay. What if I did not give you a root node?
Interesting.
How would you find the successor?
Okay.
It sounds like when you're going to the right, then that's not a concern. But what about when you need to conceptually traverse up?
Right. Okay. So let's say we're given a node, like in your example here, we want to find the successor of, say, 60, and we're just given that node 60.
Mm-hmm.
So we would have to have an implementation of our binary search tree that kept track of the parent.
Mm-hmm.
So 60 would have no children, but it would have a parent. And so we'd say, once we found our value, we could, if there were no children, then we could traverse to the parent, which might be, it could be greater than or less than the current node.
Correct. So what would be your terminating condition?
Got it. So I think that we would, okay, so let's say that we are finding the successor, we're given 60, 60 has no children, but it has a parent. So we traverse up to the parent and we'd say, if the parent is greater than 60, then we know that we found the successor, the next largest value. Let's see, if the parent is less than 60, then we would need to traverse up from that parent.
Mm-hmm. Sorry. So could you clarify, just as a quick summary, like what is the stopping point for navigating up?
Sure. So the stopping point for navigating up is when our parent's value is greater than our search node's value. At that point, we know that we found, let's see, a larger node. I'm trying to think of a case that would require you to traverse from the parent.
Oh, I see.
Okay, so there are two cases. Your parent is either larger than you or it's smaller than you. In the case where your parent is larger than you, then you know that is, and you have no children, then you know that you found your successor. In the case where your parent is less than you, then you need to continue traversing to the next parent until you find one that is greater than your search node. Okay.
Mm-hmm. Okay. I think that makes sense. Cool.
Okay, great.
What about for 80, like you were saying here? None of its parents are larger than it.
Okay, so in that case, we would end up traversing until the root node, in which case the root node has no parent. And if we get to that position, we know that 80 does not have a successor.
Okay. All right. Yeah, and I think that makes sense because even with your current implementation, the greatest element in the tree has no successor, which makes sense.
Okay, great.
Okay, cool. I think we're at 40 minutes. We probably don't have time for a second question, but I think this is a good stopping point.
Okay.
Yeah, if you can agree with that. Yeah. So in terms of like my assessment, I would say definitely like this would be inclined to hire. A lot of good indicators going on here. Starting off with a complex example to derive like an algorithm. So that was a combination of like getting clarification and doing some testing to make sure you have a plan of action before starting implementation. So definitely what we're looking for here. And really like that you broke down the brute force and the the most optimal scenario that could be possible here. Yeah, I think you might have skimped a little bit in terms of walking through examples in that example tree that you gave. You kind of had a bias for the right side of the tree, and I think later on during the implementation, you started to realize that you made some overgeneralized assumptions about when there's no children versus when there's no right child.
Right.
So I wonder if maybe you would have caught that if either you worked on the left side or maybe had a less complete tree. Like say you removed the 4 here and you tried to get the successor of 3, then that might have helped you identify that part. However, I would say that even after that, it seemed like only a minor adjustment when I pointed out that else clause that you were able to adjust and revise that pretty quickly. So I can definitely see you have pretty good problem solving skills, and you do have a good foundation, or not foundation, but methodology to tackling a problem. So a lot of premeditation before any type of implementation gets out there. You're already making sure you have a complete solution, even if that solution is not correct. You still try to flush it out as much as possible. It does seem like you do benefit from making the pseudocode, so I'd encourage you to continue doing that, however trivial it may seem after you've done everything else.
Right.
Because it does seem to help you not lose your place in the implementation, which we saw a little bit of with the code that you had wrote initially and then kind of erased afterwards and kind of rewrote a lot of this main method.
Right.
Right. Yeah, definitely a lot of good indicators. I would not weigh the coding misstep too heavily against you. It was a little. I mean, before you got any code down, I was already kind of anticipating that you would finish fairly early.
Mm-hmm.
And then during the initial code write up, I was starting to have some doubts, but you were able to recover very well. So I'm glad to see that.
Okay.
And then subsequently, you did follow up with verifying your code and being proactive about walking through it, using the examples, going through it line by line, and you were able to get a lot of confidence that your code worked mostly, short of like that one else block. And I think that's fine. Some code will have a bug or two, and the fact that you were able to identify it and adjust it was the part that I would say should be emphasized. That I thought was good.
Okay, great.
In terms of the follow-up questions, definitely really good job analyzing the time and space complexity. My follow-up questions, it seemed like you understand conceptually like what your code is doing, and you were able to pivot to these different related challenges. So I think a lot of good indicators here. I think you recognize like there's just a couple of minor things that you can do to improve even more, and just kind of give you almost like a 99% guarantee that you'll pass the coding interview. But there isn't too much criticism I can give other than some nitpicky things.
I got you. Yeah, I definitely agree. I think that as soon as I started coding, I kind of wished that I had done a little bit more pseudocode. So that's definitely some room for improvement there. And then that was conditional, but that makes sense.
Yeah. I think I don't know if I really have anything else to say. Do you have any questions for me?
Do you? Yeah. So let's see. So I have I have a virtual on-site on Friday. I think so. With Amazon, correct?
Mm-hmm.
And it will be 4 1-hour interviews. I think that there's 30 to 40 minutes slated for the technical question, and then there's the behavioral after. And I'm aware that Amazon's behavioral is unique because they have these principles that they really value, and you have to have stories that speak to each of the different leadership principles.
Correct. Yeah.
So 3 of the technical interviews are a coding algorithm, and then there's one system design question. I think one thing I'm a little bit curious about is if in your interview or any interviews that you were a part of, what if you guys did any object-oriented stuff that, like object-oriented design patterns, and what the expectations there were.
So I think that for a SD2 position, you're most likely going to have more of a system architecture interview rather than an object-oriented interview.
Okay.
Those tend to be slated more for junior candidates. Having said that, I would not be surprised if someone asked a little bit about object-oriented design.
Okay.
But I think you should primarily expect the architecture interview, not the object-oriented one.
Okay.
Yeah, and you're right. The leadership principles are heavily emphasized at Amazon as opposed to Google or Facebook that are very heavy on the technical side. They weigh that a lot more than your behavioral stories. So I think you're right. You're definitely, it seems like your coding skills are, up to the hiring threshold that they would probably be looking for, and your time would probably be better spent looking at behavioral and system design concepts.
Okay, got it. Yeah, that was my follow-up is thoughts on, what would you'd recommend for improving. So I have a system design interview coming up in an hour, and then, spend some time on behavioral stuff. And then in terms of improving, the coding questions, do you have any thoughts there?
Improving the coding, so I'll start off with the easy one, is improving the coding. I would definitely say let's have you continue doing that pseudocode so that you don't have that gap in translation between what's in your mind and what's actually written out in code. Otherwise, I would say definitely continue what you're doing, making sure you test adequately, and so that you understand all the scenarios that you have to account for. So that's really all I had to say in terms of improvement. I would say continue what you're doing now, because everything you did other than that was important and a good demonstration of thought process. Now, system design would probably be the second easiest thing to talk about. So I would encourage you to look at something similar to grokking the system design interview. It's like a online $80 course, or there are some public resources as well on GitHubs. And then there's also a YouTube channel called Success in Tech. I'll write it down here. Tech. Actually, let me just grab the YouTube link. Okay. So this kind of gives you a demonstration of how to apply those concepts, rather than purely teaching you about the concepts. And I like it because it's a good demonstration of what you can realistically do in 45 minutes, as opposed to the grokking the system design course. It's a little bit heavy in terms of how much they cover, and so it leads to an unrealistic expectation that you should be able to go into that level of detail within 45 minutes.
Got it.
Does that make sense? I'm sorry.
No, sorry. I just clicked the link and it started playing.
Okay. So I think this is one of those free resources I found that's very similar to grokking system design, that can if you don't want to spend $80 on it and are unsure. And then system design primer. And I think this link would be good for as a reference once you've gone through this GitHub, this one kind of gives you a brief summary as a more of a refresher.
Okay.
Yeah, and I think it has some questions as well that you can work through. And yeah, so I think you're definitely doing the right thing in terms of preparing for system design if you're going in for mock interviews. It's definitely going to be more emphasized for a senior engineer to know that type of stuff,
Right.
opposed to a junior engineer for hopefully obvious reasons. Yeah, in terms of behavioral, I think that one is going to be a lot more about just practicing using mock interviews and um, really working on your stories, making sure they fit that STAR format, situation, behavior, and impact, or action and result, same thing. So making sure that it's something kind of like pretty short and concise for the situation, and then for the behavior and impact, that's where you want to have a lot of emphasis on. Yeah, so if after this, we could connect, and I can try to provide you some other resources as well.
Yeah, that'd be great. Thank you.
Yeah. Okay. All right. I think hopefully that gives you a better idea of how to prepare. But I think you're definitely doing the right things. It sounds like, and you know what to expect.
Awesome. Last really quick question for you. Okay. So are you working at Amazon currently?
No, I'm no longer working there. I'm working at Oracle at the moment.
Oh, okay. What were your thoughts about working at Amazon?
I think you will have there's a lot of teams, so your experience will vary a lot from person to person. I think the primary thing I would say you should focus on is the team that you're going to be on, what their culture is like, and potentially maybe what their that department's organization and culture is like, because that will I think your team will dictate the most about how the quality of your experience. Yeah, so my wife worked there before me and still works there after me, so she definitely has had a better experience than I have. So it is really variable. I think one thing that I have noticed in general across the board is that because Amazon is so data driven, one of the drawbacks or benefits is that there really is a reason. There will be reasons to promote you as well as reasons to not promote you. So there is a big bias for, depending on how well your manager and folks like you, they can really drive the direction of your ability to get promoted. So it can be easy or very difficult to gain seniority in the company. So my typical advice would be, if you come in, you want to come in at a baseline where you're happy to be there for a long time potentially.
Got it. Makes sense. Okay, awesome. Well, thank you for all the feedback. Much appreciated.
Yeah. Okay. Quick question then. So where are you working currently?
I was working at a startup, and then unfortunately in April we ran out of money, and so I was laid off as a result of that. We were just kind of in the middle of fundraising, and then coronavirus hit, and our potential funding got pulled. So that's where I'm at currently.
Yeah, got it. Yeah, I mean that's not an uncommon situation to be in these days. So yeah, I totally understand. But it seems like you're still able to get interviews with these big tech companies. So I think you're doing the right thing, and it seems like you have a pretty good chance, assuming your system design and behavioral skills are kind of similar to your coding skills.
Nice, thank you. Yeah, much appreciated.
Okay. Cool.
Great.
All right. Well, I don't have anything else. Why don't we? I'll go ahead and select like yes for keeping in touch or staying in contact, revealing the contact information. And yeah, so if you'd like to do that, we can stay in touch.
Yeah, absolutely. That sounds great. I'll do the same.
Okay, cool. All right. Have a good day.
All right. Take care. You too.